Hi, I'm Mr. Rose, and today we're going to be continuing to talk about rotation. So as we've gone, we've started to build a dictionary of sorts, a set of equations that describes motion and all things that we know. On one side over here, we have my translational motion. We started with our kinematic equations, such as d equals vit plus 1/2 at squared, and then we found a rotational analogous equation, like theta minus theta naught equals omega naught t plus 1/2 alpha t squared. And we have those sets of equations. We then move forward a little bit and we learned about kinetic energy. Kinetic energy was 1/2 mv squared. Well, we have a rotational equivalent to that of kinetic energy is 1/2 I omega squared, where I is our moment of inertia. Well, then we started talking about momentum, and we have a momentum equation of mass times velocity. And we haven't gotten to this yet, but there has to be a rotational equation for that as well, where we have our angular momentum is our moment of inertia, I, times our rotational velocity, omega. Well, then we learned that if I take the derivative with respect to momentum, my dp dt, well, I know mass isn't changing with respect to that, and I get Newton's second law, F equals ma, which has really been the focus of a lot of our work. Well, if I move forward and I can take that same time derivative with respect to angular momentum, I'm going to get, you probably could have guessed this side, I times alpha, where I, again, is that moment of inertia, and that part isn't actually going to change when I take my time derivative, but what is going to change is my acceleration. So what we're going to explore today is what exactly is that torque. Well, I'll look at my picture here. We have two sets of, two pictures. If I want to first focus on my drawing in brown, I have a rod with two masses at the end, and I have a point that I'm going to pivot around that axis right there when I apply a force perpendicular to that rod. When I apply a force perpendicular to that rod, it's going to rotate. And that rotation, it's going to be rotating a very, very small amount. And that rotation is what I drew here in purple. So I drew this same mass in purple where it moves some very small angle delta theta. So I want that angle to be small because if delta theta is very small, I can go ahead and assume that my angular acceleration is constant for this. Well, to figure out exactly how it turned, I'm going to utilize one of my fundamental concepts, work-energy theorem. We know that the work-energy theorem, by definition, is a change of work, it's a force times the distance, is its change in kinetic energy. So if I start by looking at the force times the distance, well, what distance is this actually moving? The rod moves a distance of this delta theta. And if you recall from previous lectures, my distance is how far away I am from my axis of rotation, r, times that arc length, or my angle, d theta. So I know my distance is just r d theta. I put a direct substitution in, so now I know that work is my force times my distance, r d theta, is my change in kinetic energy. Well, my change in kinetic energy, going to my definitions over here, kinetic energy is 1/2 I omega squared. So if my kinetic energy is 1/2 I omega squared, a change in that kinetic energy must also be then my final omega minus my initial omega squared, all times the moment of inertia, multiplied by the half. So now I have another direct substitution where I bring down my force times the distance is equal to my change in kinetic energy, the object moving from there to there over that small angle delta theta, 1/2 I omega squared minus omega naught squared. Well, from those kinematic equations, I'm hoping this looks a little bit familiar to you. I have a kinematic equation that says omega squared equals omega naught squared plus 2 alpha delta theta, 2a times distance, which means I can subtract that out and I can make yet again another direct substitution. I have a direct substitution, omega squared minus omega naught squared, is equal to 2 alpha delta theta. Plug that in. Now I'm almost done here. I have my force times my distance is equal to 1/2 I, 2 alpha times d theta. And now I can start canceling things out to simplify. And I'm left with my force times however far away I'm applying that force from my axis of rotation. F times r equals I, the moment of inertia about that rigid body, times alpha. Now remember, this also has to be a rigid body, meaning those forces are not changing the shape of anything. Now this, by definition, is my simple definition of torque. A torque is not just some force. A torque is a force with some added component. And it's actually two additional components. It's a force at some distance r away from that axis of rotation, and there's some other component. Where does that other component take place? Well, that other component I have here is my torque is the sum of all of my forces, because torque, just like force, it obeys the law of superposition, meaning if I have many, many forces, I can find those vector components of forces and add them all up, just like every distance apart. Add all of that for my total torque. Well, now I have this sine theta. Before I didn't need it because I said, what if my force was perpendicular to the axis? What if my force isn't perpendicular to my axis? What if, for example, I'm becoming famous, I'm going on Shark Tank because I invented the door. I know it's a new concept, the door. You can see here my hinges. Even though I invented this door, someone else came along and said, I can improve your door. I'm going to put a doorknob on it. Blows my mind. Where do I put that doorknob? So if I come and I put my doorknob as close to the hinges as I can, that might be a good place for it. That might not be a good place for it. But I'm coming along here in the land of stupidity, and I'm pushing on that doorknob as hard as I can. And if I'm pushing on that doorknob where it's next to my hinges, I'm not going very far. So I need to figure out a better place to put my doorknob. I put my doorknob some distance away from my hinges, as far away from as I can. And now all of a sudden, this door works a little bit easier. So now I have that distance from my rotation point. But what if the force isn't perpendicular? That didn't actually answer that question. So maybe now that I figured out where the doorknob was, I want to think, can I make something easier? So I'm going to apply a force in that direction. Well, if the door is put together well and these hinges are there, I'm going to be pulling on this door as much as I can. The door is not going to move because that's parallel to the direction of my motion. I soon realized that the best scenario is by applying a force perfectly perpendicular. Well, unfortunately in life things aren't always perfectly perpendicular. So if I come down to here where I redrew my original drawing, here I have my two masses, here I have my point of rotation, and I'm applying a force at some other point there, but at some odd angle. Well, this angle theta is the end of my torque. That's that sine theta I. Theta is the angle between the line joining the point of application and the direction of my force. So what that means is, when all is said and done, my torque, which a lot of people may remember as a twisty force, my torque is the force I need to change the omega of an object, change that object's angular motion or its angular velocity. To do that, I need to figure out how far away r I am, what force I'm applying, and exactly how much force is applying in the right direction. So for this, that sine theta is my F perpendicular, the perpendicular component of that force. Meanwhile, my parallel component is a waste of a component that doesn't help us in any way, shape, or form. We can just throw it away. Now, one thing you might realize when you're looking at torque is the unit. The unit of torque is a Newton meter. If I think for a second, I've seen Newton meters before. A Newton meter is a joule. A joule, be careful, is not a torque. Torque, even though we have similar units, cannot be measured in joules. It's not a unit of energy. How can I prove it's not a unit of energy? Well, I come over here and I look at this simple example. Here I have a pendulum of length L with a mass, or a pendulum bob of M rather. I'm going to move that pendulum, physically move it from point A to point B where it's still mass M, and I raised it some height. This little height here, and I deflected it some angle theta naught. What I want to know is how much work did I do in order to move that bob that distance, that angle of theta naught. Well, what I did here is I'm setting up my work just because it's just me moving it. How much work did I do? I can say my work is equal to the change in gravitational potential energy. Well, if I calculate the change in gravitational potential energy, I have mgl, that's that whole length there. And then I subtract my new height, follow that dotted line, which just be mgl cosine theta. What is that cosine theta? Well, if I take any intermediate spot, I can start to draw a free body diagram on here, but let's say I label that theta. That's some intermediate spot. As theta changes, my work is obviously going to change. Well, I can summarize, and I can say that there's a component of force that's here, and there's a tangential component that is F sine theta. That tangential component, F sine theta, is actually the only force acting on it is mg. That's actually mg sine theta. Well, I didn't move sine theta, I moved the distance of cosine theta. My work is my height times my new height, and basically trying to figure out how much that I've moved. MGL minus MGL cosine theta, I can factor out an mg. I have MGL minus L cosine theta, take that whole thing out, and now I have the work done, which is my change in gravitational potential energy, is MGL 1 minus cosine theta. Now let's look at what happens with torque. Here, let's fix my free body diagram where I have mg. Again, I can see that this component of my force is going to obviously be equal to my tension, that rod. So that's going to cancel out, and the only force that I have to worry about is this mg sine theta. Now, mg sine theta is what I am using to physically move my object. So the torque we just learned is r times f, where r is the length. I'm moving it some sine theta, and there's my force. So my torque is mg sine theta times that r distance L. Well, if we recall, work in a translational motion is the force times the distance. Well, work is now my rotational motion of torque times d theta, how much that's actually going to change. If I know that work is going to change for every small little angle theta, I need to take the antiderivative, sum all of those angles up to get my total work. So here I have mg sine theta L d theta from my starting point 0 to some angle which I call theta naught, some later angle. Once I look at that, I can pull out my constants, mgl come out, I have sine theta d theta, the antiderivative from 0 to theta naught. Well, the antiderivative of sine is a negative cosine. So my work is equal to mgl times negative cosine from 0 to theta naught. If I plug all that together, I get work equal to mgl 1 minus cosine theta. What we proved earlier, mgl 1 minus cosine theta. What this means is if I could say that torque was a unit of energy, again, which we know it's not, my torque would match the work, and that clearly is not the case. Energy and torque, joules, and a Newton meter for torque are very two distinct things. Thank you for watching. I hope you enjoyed. Please remember to like, share, comment, click, enjoy, explain, anything else you can think of I'm supposed to put here, put it in the comment section so I'll read it and say it next time. Thank you and see you next time.